Regulation of circulation is actually a pretty detailed subject. It deals with how does blood flow in the body, what controls it, and a big part of that is, of course, under the nervous system and the heart. But basically, here's a good example. If you're sitting in class and you're not moving around, most of the blood in your body is pooling in veins, liver, spleen, and blood's still going all over your body, but a majority of it you're not using. If you get up and start walking or running or going upstairs, then blood is going to be shunted or relocated to your muscles of your legs, lungs, heart, brain to sustain that effort. So that's what this section is referring to. How does blood end up where it's going, and then what are some factors that control regulation inside your body? Here's the first one. They're called precapillary sphincters. Now, inside your body, muscle tissue, organs, just about everywhere you have everywhere you have capillaries that run through all of your tissues, all the tissues that make up organs. Think about all the tissues you went through in histology: reticular, skeletal, cardiac, smooth. All the tissue types. They all have capillaries. They all have to have blood and oxygen. And so on this example, here's one right here. Now, this is where a tissue bed is mostly closed off. You see there's blood flowing through here into the veins, but you see it's not spread out everywhere else. Well, what controls that are these little things that look like valves. They're called precapillary sphincters. They're made of smooth muscle. They're very sensitive to changes in the chemistry of the blood. This example here looks either all opened up. This is an active tissue. Just imagine this being a muscle, and a muscle that's exercising, and it needs max blood flow. You see all that blood's flowing through, and then here are those little sphincters, and like it says here, they open and they'll allow more blood flow. Your body's only going to use what it needs to, and if you're not, like a muscle for instance, if you're not using it, there's no need for all that blood to be going there, which is a good thing. You don't want your legs swelling up like you're doing squats while you're sitting in class trying to take notes. So, and then even there it says they are closed. So this first section is, and this is a local thing, this does not involve the heart or the nervous system. It's strictly on the chemistry level and the local level at tissues. So, what are some factors that affect blood flow through capillary beds? Here's two, and then we have little categories underneath that. Factors that increase blood flow through a capillary bed. Low oxygen, in other words, cells need oxygen, so of course it's going to increase blood flow. An increase in carbon dioxide, which is a byproduct of cell metabolism. CO2 is a toxic gas. It has to be removed from tissues that causes damage. And an increase in hydrogen ions, or acidity, like lactic acid. So any three of these factors would increase blood flow through a capillary bed. So all three of those would cause this situation here. Either low oxygen, high CO2, or high acidity. Factors that decrease blood flow through a capillary bed. If there's plenty of oxygen, right, there'd be no need for big blood flow there if there's plenty of oxygen. If there's low carbon dioxide or low acidity, low hydrogen ions. Which would be that example. If a tissue has plenty of oxygen, there's no reason for these little valves to open up and allow blood to flow through. So that's the first one. I know it says number 2 here, but so regulation of blood through capillaries. Here is a real life example. Here is Arnold Schwarzenegger talking. Well, he's talking, and I had this down so I could talk over him, but he's talking about how when he lifts weights that his muscles get this full feeling, and this is exactly the concept we're talking about here. He's decreasing the amount of oxygen in muscle, and he's increasing carbon dioxide. It's a byproduct of muscles contracting. And he's increasing the lactic acid in his muscle, which are hydrogen ions. So that is a good example of local control of blood flow. That has nothing to do with the heart, the nervous system. It's simply the body trying to meet the demands of that particular tissue. And that's what actually controls blood flow through tissue beds. All right. Here's the next one, and I just blew right by it. Starlings Law of the heart. So what that states, this is the only heart picture I have pulled up. Starlings Law of the heart says that the more blood that enters the heart, the more the ventricular walls are going to stretch, and as a result, the more tension is going to develop, and the more blood that's going to be ejected. If 120 mils of blood enters the right ventricle, you want 120 mils to be ejected. You couldn't have it any other way, or blood would back up into the system. So somebody discovered that, Frank Starling, and that's what it is. It's called a length tension relationship. The longer the ventricular fibers stretch, the greater the force with which they contract. Like it says there, it's the stretch in the fibers before they contract. And if there's less blood entering the heart, the ventricular fibers the muscle is going to stretch less, and then you'd still have the same amount being ejected. It's to make sure you have constant, same volume of blood leaving that's entering. And like it's saying there, it's a length tension thing. The more the fibers stretch, the stronger the contraction. As a result, the more blood entered, and then more blood is going to be ejected. You want the same amount leaving that came in. That's called Starling's Law of the heart. Now this one. This one's kind of detailed. And this is the picture out of another textbook. So up here is the cerebrum. This down here was the medulla oblongata. If you watch The Water Boy, you'll never forget where that is. This down here represents the spinal cord. These are paravertebral ganglion, and these are out here, and then these are the trunks, the paravertebral ganglia. They're part of the sympathetic nervous system. You can see that at the bottom it says sympathetic trunk, and then it has fibers of the sympathetic nerves. And you see they come up and they innervate the SA node, the AV node, the bundle of some Purkinje fibers. So that's how they can affect heart rate. It's because there's direct nerve innervation in those areas. It can speed up heart rate or slow it down. These nerves can. Fibers of the parasympathetic vagus nerve. Okay. The fibers of the sympathetic nervous system are called accelerator nerves. They're part of what is called the cardiac accelerator center. The fibers of the parasympathetic division, they travel along the vagus nerve, and they're part of what is called the cardio inhibitor center. And see, these coming back this way, these are all sensory fibers. These are baroreceptors in the carotid arteries, carotid sinus, and then you have some here. Those are very sensitive to stretching and blood pressure changes, so that information is going back to the brain. And in the medulla is where all these cardiac accelerator inhibitor centers are found, along with the ones for the arteries and veins. These innervations up here, how they travel down this way, and they're also connected to the cardiac center. This is why people faint. Sometimes what you see can affect your heart rate. Or, people fainting is basically vessels dilating and blood pressure dropping. But yeah, just saying what you see can affect heart rate because there are nerve innervations that go down to that area. So the cardiac accelerator center sends impulses along these nerves. They're going to speed up heart rate, speed up how strong the heart contracts, all of that. The fibers of the parasympathetic nervous system, see it's coming out that way, they do the opposite. They're going to lower heart rate, lower blood pressure, lower the contractility of the heart. And your brain is basically always juggling that. But here are the areas where, because the heart has its own impulse, it does not need direct outside stimulation. But to raise heart rate and lower heart rate revolves around that area of the brain. The cardiac inhibitor center, the parasympathetic part, the vagus nerve, that lowers heart rate. The fibers of the cardiac accelerator center, or the sympathetic nervous system, increase heart rate. Intrinsic system, the sympathetic nervous system, the accelerator, increases both the rate and force of the heartbeat. The parasympathetic acts like a brake. They're found in the medulla oblongata. That's the area they're located with. The accelerator nerves are part of the sympathetic nervous system, and the inhibitor nerves, or cardioinhibitory center, is part of the vagus nerve, or the parasympathetic nervous system. And they're both found in the medulla oblongata. And there's that same picture. See, I probably could have made it a little bigger, but see, there's where the little sensory fibers are attaching. And then you can see there's the parasympathetic innervating. Here's the sympathetic. So basically, this is how heart rate is increased and decreased. The SA node sends out a constant signal, but a person's heart rate depends on what's going on with these nerves. I'll make this very quick. The Vasomotor Center has to do with blood vessels. So these are the carotid arteries. This is the left subclavian. This is called the brachiocephalic artery, which would go into the right subclavian. Here are the veins. The Vasomotor Center is also found in the medulla. It's all sympathetic. A drop in blood pressure would increase sympathetic nerves to constrict arteries to offset the drop in blood pressure. That's why it's called vasoconstriction. If blood pressure is high and there's a point where you want arteries to dilate, there'd be less sympathetic nerve stimulation and the vessels would dilate. That all happens at the Vasomotor Center. And it's all sympathetic. There's no parasympathetic nerves involved with arteries and veins as far as them constricting and dilating. Vasoconstriction means a decrease in the lumen, the inside. Vasodilation is an increase in the lumen. In other words, an increase in size and more blood flow. These are potential things that affect heart function, blood flow. Potassium ions, they can alter the heart cell membrane permeability. Too much potassium would actually stop the heart. And you remember the whole potassium ions flowing out and sodium flowing in? That's kind of what that relates to. Calcium ions affect how strong the heart contracts. It's called the forced contractility of the heart. The heart relies on extracellular calcium. And so that has a big play on blood pressure. A lot of blood pressure medications are trying to limit calcium ions, so the contraction is actually weaker, lowers blood pressure. Sodium ions affect how much blood volume a person would have. Remember, where sodium goes, water goes. That's where aldosterone, the hormone, comes in. It causes the kidneys to reabsorb sodium ions, so a person would have more water in their body, in their blood. Nitric oxide is a chemical that is released from these large vessels here in response to blood flow. It actually increases blood flow. So anyway, that's a pretty strong chemical. Oxygen, we talked about that. Too much or too little oxygen affects where blood is going in the body. Low oxygen is going to stimulate the brain to send out more signals, to breathe more, higher heart rate. Carbon dioxide and hydrogen ions affect the brain the most. If these levels are high in blood, a person's heart rate's going to go up and their breathing rate's going to go up. Because the whole goal is to get that to the lungs so that it can be ventilated off. Blood vessels. Last thing. Okay, this little circuit, arteries to arterioles to capillaries to venules, which are small veins, larger veins, and then back to the heart. That is a pathway. So you need to know this little pathway and some basic parts of arteries and veins. Okay, structure of blood vessel walls. Now, I do have a really good, this is out of a high-end textbook. This is an artery. This is a vein. Some veins have valves. The one in the periphery, they prevent backflow because the pressure in veins is so low. This represents capillaries. Right there, remember we just kind of talked about those. That's a whole network of them. Capillaries are the smallest and the thinnest of all the vessels. But here are the layers of an artery. First of all, you have this outside layer called the Tunica Externa. It's made of collagen. It actually stretches. This middle part there is the tunica media, which in an artery is thick. Artery walls are under high pressure, so they're actually thicker as far as the walls go. And the tunica intima, now endothelium is simple squamous epithelium, is this inner layer here. Very delicate, high blood pressure damages that. But those are the three layers of an artery. You have the same three layers in a vein. Here's the tunica intima. The tunica media is this thin layer. It's still muscle, and I didn't mention this, but the tunica media is smooth muscle. It's a lot thinner in veins. Veins have much thinner walls than arteries do. So the inside of a vein, most of the time, is larger. It can hold more blood. And then this is called the tunica externa, and all this little stuff in here are nerves and arteries and veins. And that's a capillary. So thinnest vessel allows gas exchange. It's all endothelium, simple squamous epithelium. But a couple of things about arteries. Best definition of an artery is that it takes blood away from the heart. There's the layers that I went over with you. Capillaries are where the gas exchange takes place, oxygen and carbon dioxide, things like that. And then veins. Veins actually in the extremities have valves to keep blood flowing one direction. And they can hold more blood. They're bigger, but they have thinner walls. And the pressure inside a vein is almost nothing. So, in fact, veins rely on arteries. The heart is pumping blood through arteries. See, veins have the same three layers. It's just the media of a vein is very thin. But veins rely on breathing, pushing down on organs when a person breathes, vasoconstriction of vessels, and then muscle contraction. See how these muscles are contracting? Here's a vein that's closed. There's the one that's open, and it's squeezing blood that way. And then this would close behind. Veins rely on that. There's very little pressure in a vein. So a person moving around, breathing, like I said, vasoconstriction, which means the walls, the smooth muscle walls, not this, but the smooth muscle walls are contracting, this tunica media part, and it's squeezing blood back to the heart. This is a pretty cool picture. You can see, okay, there's the intima, here's the media, here's the outside, the tunica externa. See the veins inside the valves inside the vein, the tunica intima, the media, the outside. You can actually pull this around like that, and you can see how thick an artery wall is and compared to how thin it is there. I got one more. Same thing here. Look, see how thick that is compared to this vein side, which is way thinner. This one actually has the little capillary bed. See, there's blood going across, unloading oxygen, and picking up carbon dioxide. That's why it's got the blue color. Same thing. This one has the vein over here. There's the intima, the media, the outside, the externa. Here's the intima there. There's the media. There's the externa. But that's a little information about arteries and veins. All right, so thanks for listening. I appreciate it.
And that's the bottom line, because Stone Cold